I'm going to do an experiment with you. So everyone, do me a favor and close your laptops, at least for 5 minutes. Thank you. All right, you ready? If you've done this experiment before, if this looks familiar, keep it to yourself. Don't spoil the others. It's a very powerful effect when it works, so I want everyone to have this experience. OK, here we go. Ready? A boy and his father are in a car crash. The father is killed instantly. The boy is rushed to the hospital and prepped for surgery with one of the best surgeons in the country. Lucky him. Doctor arrives, sees the boy on the table, and says, "I can't operate on this patient. He's my son." Now, when I first saw this myself a couple years back, I was absolutely stumped. Like my mind just like raced to explain the paradox. Like I'm sure right now in your minds, like you're coming up with explanations for this. So, who is the surgeon? Michelle?
There's a simple explanation for this, and it's the mother.
Raise your hand if you've seen this for the first time and you immediately knew the mother was the answer. 1, 2, 3. 3. OK. That's a little bit lower than average. Typically, 85% of people are stumped by this, which means, I guess by extension, like more than 3 out of this room typically get it. But don't feel bad. I was also totally stumped by it. Michelle was totally stumped by it. You are just a good learning machine. You've been trained your entire life on a stream of very, very good data that supports the prior that surgeons are men. So, that's cognitive bias. The reason that felt hard was because you have cognitive bias. We all do. And so the goal, and we're going to describe one of these, is to find technologies that can help us identify these biases that we have and help us reverse them. So here's a system that's built on human decisions. So Wikipedia is an example of a web-scale system where it's really just amplifying the individual decisions of individual humans. So what happens is all those cognitive biases in those brains get inherited by the web-scale system. You just can't avoid it. It ends up happening. Let me give you some examples. But before I do, I just want to emphasize the astounding thing about Wikipedia is that it works at all. So I'm going to be pointing out some well-known problems with Wikipedia, but that's by no means a deal breaker. I use it every day, I'm sure, like most of you do as well. It is the world's most important first point of information about most topics. And yet, there's absolutely no one in charge of this thing. It's really just a big volunteer effort. Millions of people deliberating with each other to reach consensus on facts about the world worth knowing. So let me give you an example. So if you've never heard of Donna Strickland, I hope that you'll never forget her now. So last year, she won the Nobel Prize in Physics for her work on laser physics. First woman to win this prize in 55 years. It's a big deal. On the day it was announced, the world was astounded to discover that she had no Wikipedia page. She now has a very long, very detailed Wikipedia page. Like, I can't even capture the entire table of contents on the screenshot. You may be surprised to learn that all that information that you can now learn about this person did not appear overnight. It is not the case that she won the Nobel Prize and suddenly there was all this information available that was really significant and notable that deserved a Wikipedia page. It was always there. Somehow we just missed it. Let me also point out that on that very day, this fellow won the same prize with her. This is her co-laureate. He has a much less detailed page, but it has existed since 2004. Let me show you an example of a typical web page, a Wikipedia page about a scientist. I found this guy at random just using my data. Totally typical meat and potatoes Wikipedia page about a scientist. Is based at some research institute, studies a certain topic, and has some public impact. They're citable, reputable news sources about this person and his work. And so you get a Wikipedia page. Totally normal, nothing controversial here. Now, in the same query where I found him in my data, I found a colleague of his who works on almost the same thing, very, very similar topic, public health. There's actually more to say about this colleague of his. I would love to show it to you, except it's pretty hard to fit it on this screen. Her name is Amizota. And the reason it just won't fit on the screen is because there's this huge warning banner stuck on her page. This is basically the process by which Wikipedia pages get deleted. So the community basically, first it starts in the talk page where they say, this person just isn't that notable. Then someone decides to slap a big banner, and eventually, essentially, this gets fixed or the page gets taken down. So there's no bad guy here. There's no evil group of people out to delete scientists from Wikipedia. These are good citizens just trying to keep Wikipedia standards high. But the problem is it's a subjective decision. How do you decide whose page is not worthy of the world knowing? You just have to use your gut. And that's just an invitation for your cognitive biases to have an effect. So I also want to show you an example of the opposite effect. How many of you have ever heard of sting? Now, take your hand down if that sting was the singer. Anyone still have their hand up? Oh, very strong, very strong. OK, I want you to keep that in mind. But here's an example of a scientist who has the longest and most detailed Wikipedia page of all. So there is no female scientist who even comes close to this. And it's not because it's the most important scientist in the world or her work is that important. It's because her life intersects with a topic that people just pay a huge amount of attention to, namely the post-9/11 war on terror. So this is just to show you that over-attention can also be a result of cognitive bias. Now, here's your favorite sting. Her page, the one I just showed you, was 10,000 words long. This one's 20,000 words long. And in fact, of all the occupations of people, the occupations that have by far the most attention, about whom the most details are kept on Wikipedia, are updated the most zealously so that every little micro detail that you can update them on gets updated, are definitely not scientists. It's professional wrestlers. And it's not because professional wrestling is far and away the most important thing about people or the kind of people that you most need to know about. That's Wikipedia for you. It's a crowdsourced knowledge base. So the things we care more or less about get diminished or magnified. It's an imperfect lens on our world. And that's OK. But wouldn't it be great to be able to map out this bias? Before we can fight against our cognitive biases, you have to know even what they are. How do we get the tools to do this? So Michelle and I have talked about this a lot. If you're going to build a machine learning system, it's really helpful to imagine you're the machine. That's really the best first step. Imagine you're the computer. What is your task? So let's say that you're the computer, and your task is to identify all of the people who should be on Wikipedia and those about whom we're paying more attention than the citations deserve. Where would you even begin?
Well, first you'd have to look at all the existing Wikipedia pages. There are 5 million of them.
In English, yes.
News articles are being published every day, so thousands of news articles on a daily basis. You'd have to read all of those.
Hundreds of thousands in English alone.
Come up with the important information in one set that doesn't exist in the other set. Kind of impossible for a human.
And do the diff.
That's a lot.
So yeah, really, really sucky task for a human. We have on order of 1 million volunteers trying to do this. It's the largest such effort in the world, and totally not keeping up with it. They've measured the latency, for example, when huge things happen in the world, like, and they're printed in newspapers. How long does it take before they arrive in Wikipedia? It's long. Like, it takes a long time, unless it's about professional wrestling, in which case it's instantaneous. So this is the kind of data that we need. So this is an actual screenshot of the data that comes from this system called Quicksilver. So I'm at a startup just up the street called Primer. And what this thing is doing is it's reading all the news in a few different languages, but everything I'm going to talk about today is about English. And it also reads Wikipedia, of course. And what it's doing is it's extracting facts about the people and then writing summaries about them. And so this is what we need. So how many of these people actually are described in Wikipedia? So now what you have is a ranked list, right? You can sort how much did we learn about these people, in this case scientists, in this case female scientists. How much did we learn automatically with an AI system from the news versus how much is known about them in Wikipedia? Ta-da! Hardest problem effectively solved. So when we first started talking about this, when we got a lot of coverage in Wired, for example, last year, we being Primer, were like really, really proud of this. Pretty much smug. Because we only had like, tens of thousands of people being tracked with on order of, hundreds of thousands of news docs. And we did it from static JSON-L files. So really, really not scalable. And so since then, we've basically been getting the system onto Kubernetes and trying to make it actually work at scale. And we immediately started to run into problems. And Michelle came and gave us a consultation.
Yeah, so when I first got my hands on Quicksilver, I set out to look at the existing architecture, figure out how it was built. It was originally a set of separate pieces running in a hand-rolled Kubernetes cluster on AWS. And I had one key question for John. As you scaled the number of people you were looking at, what kind of performance were you seeing?
Bad.
Yeah, so it seemed fine with just the first few thousand, but as you started to grow to Wikipedia scale, you ran into challenges. This is a very familiar problem. You have this handcrafted artisanal ML system that's been meticulously sculpted for solving a tangible problem. You have a relational backend, a document store, a caching layer, and a monolith that coordinates between all of those pieces. With that as a starting point, the first thing we do is forklift it into GCP. Some of this was easy. For example, moving the Kubernetes manifests onto GKE was straightforward. Thankfully, you were already running Kubernetes. We moved some of those application config files into config maps and database credentials into secrets. We even moved the document store from Elastic into cloud storage. Elastic was overkill for this application, so we used the simplest storage we could find. But other things were a bit harder. When you stand up your application, what's the first thing it does?
Yeah, so step one, hit Postgres and talk to the knowledge base. And that's also step N. It basically has to iterate back and forth, back and forth, back and forth with SQL calls.
Yeah, so I noticed that. Actually, moving the data from Postgres into Cloud SQL was just delightfully straightforward. But connecting to it was another story. So if you haven't used Cloud SQL before, if you want to run an application inside of Kubernetes engine, you need something called a sidecar that gives you a proxy, a connection proxy. And what it does is it creates a network tunnel. It continuously refreshes your SSL certificate. It can be a bit tricky to set up, but once you get it running, you generally don't have to think about it. OK. So now that we have it running in GCP, great. Now you have two problems.
Yay!
Your application runs poorly on two different clouds.
Mission accomplished. Yeah, so it is still like directionally correct though, because although we're talking about scientists and Wikipedia as a motivating example, we're actually building products. So what our customers want is a system that you can just feed in natural language documents. It will automatically stand up a knowledge base and update it as it learns things from those documents, and then describe itself in natural language reports of some kind. and always comparing itself to some source of truth. So that's the generalizable system we're going for. And so we want this thing to be able to deploy on any kind of cloud or on-prem, actually. A lot of customers need this to work on-prem. So if we can make it work in both AWS and GCP, it's definitely a step in the right direction.
OK. So the Primer team did this the hard way. Sometimes a monolith is OK. But in your case, having a design template would have helped you build a scalable application from the beginning.
OK, but just note that Kubeflow did not exist when this project started.
Yeah, so it's not too late. Kubeflow can still help. So let's look at how. I prepared a recording for today. What we'll be doing is spinning up clusters and watching nodes scale up and down and performing training, which is about as exciting as watching paint dry. So we'll skip over some of those boring parts, and we'll start by looking at our empty GCP console. So from a blank slate, the question is always, where do you begin? Primer was brand new to GCP, so we started with an empty project. And what we need is a way to create a fresh cluster from scratch. Well, good news, there's an app for that. It's called Click to Deploy. And if you go to deploy.kubeflow.cloud, you'll find this form. We need a couple pieces of information. We have our project name. We need to give our deployment a name. Let's call it QB.
Let's.
Give it our OAuth credentials. If you're not sure how to create those, there are instructions on the left. And that's it. We're using the very latest version of Kubeflow. It was just released last week. So how many people here have used Kubeflow before? OK, of those, who installed it themselves? OK, all right, one person. So you understand exactly how hard this is. This application is getting rid of all of that hard work for you. What it's doing is spinning up a GKE cluster. It's setting up the project, creating service accounts, enabling APIs, and installing all of the Kubeflow components. You can watch those install. It takes about 5 minutes to get to this point where you have everything running. But it gives you a public URL. That takes about another 10 to 15 minutes. And once that's up and running, you can go into your services tab, find your ingress service, and just click on the link that it gives you. So what you have now, this is your central dashboard, and this is the entry point into all of the sort of Kubeflow UIs. Now that's the official installation. That's what you get if you just use the app. But I always do one extra little step for my clusters. I'm going to show you the sort of secret backdoor feature. It's one of my favorite GCP features. It's called auto provisioning, and it's a GKE beta feature. So if you run this command, you can specify maximum limits for CPU and memory. And what it does is when you run jobs on your cluster, it will scale the number of nodes up and down based on the requirements that are there. So this takes about 5 minutes or so. But once we have it up and running, we don't have to think about the size of our cluster. So if we take a look at the number of nodes that we start out with, we've essentially created a baseline. We have a node pool with 2 nodes, which is enough to run all of the base components and a few extra jobs. So we're starting off with just these 2 nodes. OK. So now that we have our running installation, what exactly does that mean? So we just saw deploy.kubeflow.cloud. If you want to try it yourself, you can go there. We had a number of different components. I'm just going to refer to them as ingress. There's a lot going on behind the scenes. We'll talk a little bit about it later. But ingress essentially gives us that public IP, and it's a single ingestion point into our cluster. It handles all of the auth so that nothing inside the cluster has to think about it. From there, we saw the central dashboard, and that gives us access to all the other dashboards. We have some for training, some for running our pipelines. Argo is the workflow engine that powers pipelines. Katib is a way of performing hyperparameter tuning. And then we also have a notebook hub. We have operators for running training jobs in a distributed way. Argo helps us run our pipelines. Katib helps us with hyperparameter tuning. And once we have our trained models, we can serve them. We have a few components that help with that. TensorFlow for TensorFlow models, and Seldon for any Python model. So at this point, we have a blank Kubeflow slate. Now, how can I take an existing application, Quicksilver, and run it in Kubeflow? So we can take your existing manifests and apply them to our cluster, but not from a terminal. What's the language that your application is written in?
Python.
And what about the rest of the code base at Primer?
Pretty much Python.
It's all Python. So you have all of this Python expertise.
Yeah.
Let's use Python.
Yay.
So this is what it looks like to run our monolith on Kubeflow. We create a pipeline, and each step is one of our components. Let's see it in action and run our monolith as a pipeline. Okay. So we'll start by going to the pipelines dashboard, and there's nothing there yet, so we can upload a file. We can create a pipeline using Python. So we have a few Python files here. We'll look at the monolith version. And we start out by importing our libraries and defining the image that we want to use. And we set up 2 distinct steps, and we compile those into a pipeline. We're using this pipeline decorator, and we set up each step and the order we want them to run in. And then those last 3 lines is what compiles it into an archive file that we can then upload into our cluster. So we have our caching layer, our monolith step, and if we just compile it as is, we'll get a file that we can bring into our UI. But what's inside that file? This is Argo workflow definition, so it's really detailed and long. You can open up that file. It's all text. It's not binary. But you can upload it directly as is.
And you didn't have to write it.
You didn't have to write it. You could use the pipelines SDK. So if we upload it, we can see a visual representation with 2 steps, caching and then our application. And if we want to run it, we give it a name. And this will actually execute it on our cluster. So we can view it executing from this UI, including accessing all the logs. We'll see what that looks like. So our Redis container, it's pulling the image, it's creating it, and then it stood up our application.
This is my favorite part. I think this UI is really beautiful.
So there we have it. Oh, this is the bare minimum. So at this point, Quicksilver can handle daily workloads involving scientists. But for a generalizable solution, what kind of scale do you need?
Yeah, so I mean, if we're going to power all of Wikipedia editing for anyone in the world who wants to track some entity, some Wikipedia page, and have the news automatically be processed and give them updates on what's new, then definitely we're talking about web scale.
So there's no getting around it. I hate to break this to you, but you need to carve up your monolith.
No, don't carve up my monolith.
So this is where Kubeflow components can help. Now, this is what that looks like. It's a longer pipeline now. It's split up into smaller pieces. You have a data ingestion phase, and once your data is there, you can begin training. And you can do that in parallel, separately. Once that training is complete, you can serve those models and then stand up your web app. So that's the concept. How do we actually implement that? Let's kick it up a notch. How can I take an existing pipeline and make it better? Okay, audience question, what's the best tool for quickly iterating on a Python file? What are some of your favorite tools? Jupyter Notebooks. Excellent answer. All right. Where did the mouse go? Okay. So we'll start by going to the Notebooks tab. You read my mind. Okay, so what's better than hosting your notebooks locally and competing with all of your open browser tabs for resources? Running it on someone else's resources. That's right. That way you have room for all the cat memes. So what we're doing here is Kubeflow provides this spawner, and we can spin up our very own Jupyter Hub instance. This takes about 2 or 3 minutes. But this is all running inside our cluster. So we can access it locally. We connect right here, and we have our own instance. So we'll go and we'll find our microservices notebook. We'll upload our own file.
This is also really great for reproducibility. I can point you at the exact notebook where I ran everything. You can see how I got it wrong.
Okay, so fun fact about notebooks. The very first time I saw a notebook, I was in Paco's workshop. This was probably 2013, 2014. I don't even know if he knows this. But I learned everything I know about notebooks from Paco. That was the very beginning. So you're seeing this in action here. Okay, so this is our microservices version of Quicksilver. The first thing we do, we're just using a stock TensorFlow image. So we're going to install Kubeflow pipelines on top of it. And then we import those libraries. We define some static variables, so which images we want to run, which versions. And then we retrieve our database credentials from secrets. That way nothing is hard-coded in GitHub anywhere. And then we define each of our steps. We ingest our data first, and then we train. And this step is kind of interesting. It's doing some unique things. So we're making requests for resources. We're saying that we want a couple of CPU cores and 32 gigs of RAM. We're grabbing those database credentials, and then we're adding our sidecar. This is what gives us the connection to Cloud SQL. This is a brand new feature. Thank you to Eterna2 for committing that like 2 weeks ago, just in time for me to get this prepared. This is one of my favorite things. So this training step, because we're requesting resources just for this one step, that means that we don't need it for the entire pipeline. So being able to specify it at a step level is what helps us to scale out our cluster. So we compose our pipeline, we define each of those steps and the order we want them to run in. We generate our archive file right here in the notebook, and we can actually kick it off from here as well. So we have a link that brings us directly to our pipeline's dashboard, and we can see our pipeline running.
Ta-da.
So our data ingestion ran just fine, but our training job, I know that's small. It says this step is in pending state. It's unschedulable, insufficient memory.
Call DevOps.
Okay, so what do? Let's do some troubleshooting. We'll drop down to the container level. Let's see what's going on with our training pod. We have a few more details in here. And it looks like, okay, so we couldn't schedule it, but triggered scale up. This is a good sign. This means that our auto provisioning is kicking in. And because we only had 2 nodes originally and we wanted more RAM than was available, we can see this happening. If we go into the console, we can see a node spinning up.
DevOps is already on it. Didn't even have to call them.
All via
DevOps.
Python. So that all happens in the background. And as soon as that node becomes available, that'll take a few minutes. Our job will complete. And then the rest of our pipeline can finish running. Well, because what's better, having a fat cluster up all the time or having a fat cluster up just for a few hours? Okay, so the cool thing is that once that pipeline is done, the nodes disappear. So the node pool that was stood up gets deleted, and our application is up and running. Okay, so I talked about the ingress component, and I told you there was kind of a lot going on behind it. One of the cool things about it is that there's a reverse HTTP proxy. So we can just add a route to our external URL and navigate to /Quicksilver. And we can actually see our application up and running.
Yay, there it is.
All right. So what has Kubeflow given us? We've gotten portability so that we can run on any Kubernetes cluster. Kubeflow is entirely open source, and it uses vanilla Kubernetes APIs. So as long as you're running open source Kubernetes, you can run Kubeflow on top. That means you can run it on another cloud, on-prem, or even local. There's no vendor lock-in. We've also gotten scalability. So that means that our costs can grow in line with our user growth, and we can be very fine-grained about that. And then we also have composability so that our ML design can handle web scale. As platforms like Kubeflow make it easier and easier to build ML applications, it's our responsibility to build ethical ML systems. A revealing bias can have a positive effect immediately. Now that we have our system up and running, what can we expect to happen when we ask Quicksilver what it knows about a fellow speaker?
Yeah, so when I saw that login screen, by the way, just like weeks ago, literally, I was very excited. To test it out, we have been actually taking the speakers of this very event, just little bits of information about them, really, just like name, employer, as tuples, keywords if you have them, but really like it works just with name and employer, and feed them into the system, and it reads all the news for the past several years at least. And it tries to find everything it can about them and assemble together a profile. And then it hits Wikipedia and it's like, well, how much do I know compared to what Wikipedia knows? And so yeah, we actually we found someone who like popped right to the top when we ran this. So she had been pretty quiet in the news until mid-March. March 14th, in fact, is when things just like exploded. And anyone know the significance of March 14th? Pi Day, yes. So there is an engineer at Google named Emma who calculated 31.4 trillion digits of pi, breaking the world record very easily. And like there was just a ton of news coverage of this. She did it on GCP. It was a cloud computing feat. And sure enough, as journalists basically did their job of describing this, this scientific feat and describing the scientists behind it, you started to learn more and more about Emma. Lots of little bits of string that the AI system gathered together in order to have a bunch of cool things to say about someone. Now, this was trained on Wikipedia, so it's essentially like its model of what counts as interesting is everyone on Wikipedia. So it's just finding facts that kind of basically are similar to that and assembling them. And can we run it? Yeah. So this is us actually getting her profile from Quicksilver, and ta-da! There she is at the top. And this is what the machine just like spat out. Hey, there's Emma. I know about her. And if you have the job of keeping Wikipedia up to date with the latest people in the world of science and what they're up to and the discoveries they're making, this is the hardest step. How would you even have found Emma? Like, unless you're literally reading all the news every day and just keeping track of every single scientist ever mentioned, and then visiting Wikipedia to find out what you missed. That is like an impossible task. So today, actually, as of early this morning at night, this is now public. So all of you can go to that URL at the top, quicksilver.primer.ai, and we are just updating this every day automatically. And so once upon a time, what we were doing was I would generate these spreadsheets of data about scientists using Quicksilver, and then I would help people who run editathons. So that's basically you get a bunch of people and you give them pizza and beer and you edit Wikipedia as quickly as you can to improve it. It's an editathon. And it's really, really hard work. It's surprisingly hard work. And just those spreadsheets of data output were incredibly useful. That's what everyone says. We ran them in New York, London, Washington, DC, and the feedback was just like very, very positive. Like, this kind of data is what we need. And then last week, we actually had an editathon just down the street using these completely generated profiles. Because one of the pieces of feedback I got was, those spreadsheets of data about people is handy, but it's still pretty hard to read. Like, what we really need is to just have the computer write the first draft of the Wikipedia article. Can you do that? So we did it. Now, essentially, you can go here every single day, and it will just find people that it has detected as having lots of information in public citable sources, where that information seems to be missing from Wikipedia. So now, like, anyone, anywhere, anytime has that first really hard cognitive bias problem of what to pay attention to in the first place solved, at least for scientists.
Okay, so is Emma on this list? Does she have a page?
Yeah, so I'm very proud to say that Emma now has a Wikipedia page. And this is a good one. So remember I showed you that Wikipedia page of the scientist from Harvard? It's kind of like modest, no image. This is a better page. It's actually got more sources. It's really well interlinked. All those blue letters are basically like wiki links embedding this page within Wikipedia's knowledge graph. That interlinking is really important. So this is a good page. However, I kid you not, within 2 days of this page getting created, which by the way was made by Jess Wade, all credit due to her, a collaborator and friend based in the UK. this started to appear in the talk page of Emma's Wikipedia page. So
Okay, let's zoom in on the logic behind that.
this is how the door gets cracked open. This is the very beginning of the process of deleting someone from Wikipedia.
Okay, so the reason this person gave for wanting to delete Emma's page is they say that the computation may be notable, but that is not enough by itself to make the person who did it notable.
So it's a bit of a paradox, right? If all you're famous for is like winning the Nobel Prize, like really just the one thing, it just doesn't quite make the cut. And again, these are not bad actors. These are just people like one of the many volunteers just trying to keep Wikipedia's standards high, but it's a hard, like, subjective task to decide what the world should and should not know about.
Paco, please join us on stage.
So we're going to do something with you here now on this public stage at a public event. We are going to introduce to you the first ever Notability Award. We call it the QB.
The QB.
And it is given to a person who has abundant, significant information in public citable sources about their life and work. It's a computationally generated prize. I think AI can start giving prizes to humans that it learns things about. And the first ever QB
Thank you very much.
goes to, wait, you don't know who won it. No, it's not going to him.
The very first recipient of this
Yes.
award is sitting amongst us today, right here in the audience. Who could it be?
So let me open this
One
up
of
here.
you
This
is
is
gonna
going
win
to
the
be
prize.
audited. I'm sure Deloitte
We will
looked
invite
through
you
the,
up to the stage.
Okay, rip this open. This is a very exciting moment. The first ever Notability Award goes to the one, the only, Emma Haruka Iwao. Please join us in welcoming Emma. Come on up.